Right. Proofs in the browser.
Yes, so
Proofs in the pudding.
it's a pleasure to be here. So today I'm going to talk about why we should be using web technology to make peer improvers. My intention is by the end of this topic display, I'll have annoyed everyone in the room by saying their technology is old. Okay, so there is some movement in this space. So we have these. Lean have gone JavaScript first. We're going to have it transpiled directly to JavaScript, which is brilliant. So we're able to do things with having demos in the browser. So having demos in the browser is amazing because it means you don't have to faff around trying to install something on your machine to get to know the system. So it's just one fewer step in the process of deciding if it's worth learning to use this tool or not. So I've used the Lean system a bit, not so much this cock one, but I've used Lean and it's good fun. It worked properly. So another example of a more advanced system in the browser is this thing called Globular, which was made by Jamie Vickery, and I think this is awesome. What it's for making proofs in higher order category theory, in higher order strict category theory. About so here it's proving. So what you're seeing here is actually a proof that Frobenius algebras are associative. So I'm going to very, very carefully tell me if it goes wrong. We okay? We're okay. Okay. So this is a representation of a term where you have the output at the top, and we have three. So we have this black dot's the product. So what we can do is we can say, we've defined our rules here about how these should behave. So for instance, this rule here says if we have this S shape, then we can transform it into this spanner. Okay, so using these rules, we can we can look at what it means for this to be associative. So at the end, we'll have a tree, but with true branch on the other root. Okay. So you can kind of see what's happening here. So we're kind of shifting things around. So here we're just using the fact that we can do this with categories. And then we're going to use the S rule here, S to spanner. See, it became a spanner. And then we're back to here. So I think this is awesome because it does a lot of the stuff that Quantomatic does, which is a prover for the desktop for reasoning diagrams. But Jamie Vickery's made this program which does that all in the browser. You don't have to install anything. I think you can log in and look at other people's work because it's all on the cloud. I really think this is the future of peer improving. And another final cool thing you can do is you can project out. We can look at this proof, which was a series of slices, and we can look at that from the top. So each green, so the green, the red, and the blue are different applications of the rules here. So you can see a high-level proof as well. So with the use of web technology, we can make these really elaborate user interfaces where you can clearly see what's going on, and they work anywhere because they're in the browser. So for instance, I think I can drag this up as well. So because it's in the web, doing this kind of thing is very easy because it's very well supported. So my application is on this tab, which we'll see later. Okay. So why should we use these technologies? So I've said user interfaces for ITP need an overhaul, which is quite a controversial statement, I think, because there are already lots of brilliant interfaces for all of these provers. Problem, when I say overhaul, I don't mean just make the icons look pretty and change the fonts and then put rounded rectangles where square rectangles were in the past. I mean use these very well thought out design principles in a well-developed framework that's modern for use with to make it easier to think about these problems and to make it as simple as possible for users to use these tools. So it's easy if you're a computer scientist and you've been using Emacs forever, then and you've memorized all the shortcuts, then that's fine. You can get a lot done. But if you're a mathematician who might not have as much experience using these advanced editors, they're more used to just writing a plain text LaTeX file, then they might not. Then every single one of these things they have to learn, every time an error isn't understandable, every time it's not obvious how to proceed, every time you can't discover a new function, these are all barriers to the mathematician wanting to use the theorem prover. So it's important that we get interfaces right and that we try and modernize them and make them appealing to young people, to all of you. Okay. So the other complaint is when a newfangled technology comes along is, well, it'll just go away in a few years. I don't think the web will go away in a few years. It's pretty well established now. And when I say the web, I mean web apps. So using JavaScript and HTML and manipulating very complicated systems of user interface, all in the web browser. Okay, so this is my favorite quote. So I think this kind of captures perhaps why automated theorem provers are not used as much by mathematicians. It's because it's very difficult to understand what's going on to discover new things without without having previous experience working with computer systems. So this guy's amazing, and I highly recommend this short book as well. I really got a lot out of it, and it really helped me understand how basically everyone's an idiot when it comes to using a computer. Okay, so the other complaint about JavaScript is that it's not fast. Well, that's not true anymore. When I saw this graph, it blew me away because I just assumed that something like Fortran would be a factor of 100 times faster than JavaScript, because JavaScript is a garbage collected language, so that means you don't have to manage any memory. And it's also dynamically, objects are dynamic, which means I can take any object and add new properties and new numbers to it. So, so you can't use tricks using structs and things like that. So it's absolutely amazing that the compiler teams have managed to make it this fast, especially compared to Python, which is probably a similar featured language. So it's a log. This is the log chart as well. Okay, so why is that? Well, it's because we have more than three, absolutely gigantic companies working to make JavaScript as fast as possible and to make it work absolutely everywhere. So we can piggyback off this amazing infrastructure that's been built because of the web taking over the world. And the other problem is, well, I've already written all my code. It's already in Scala or in C++. Well, that's fine as well, because there are tools that let us transpile to JavaScript. So in particular, mscripton can take anything which gets inputted into the LLVM, which is a famous compiler chain, and we'll convert it to JavaScript, and we'll also convert it to this thing called WebAssembly, which is a kind of abstraction on assembler for the browser. So it should be possible to get very, very fast code using WebAssembly. I couldn't find a good ML one, I'm afraid. Sorry, Isabel. Maybe there is one.
There isn't.
Okay, and the other thing the other trend that we're seeing towards JavaScript is that we're getting these new editors coming out, which are very popular, which are written using JavaScript. So all of this editor is written in JavaScript, and it's basically running. It's essentially a Google Chrome tab, but without the Chrome. It's just and it has all of the features that a modern editor would be expected to have. So you have code completion, command palettes, things like that. So we're starting to get there with these tools as well. So we've got Lee and Isabel and Idris are starting to support Visual Studio Code and Atom. Again, I put this in just to annoy people, really. Okay, and also I found this very amusing.
You will see you old sometimes, so you will get this kind of talk you
Yeah, I
will get
know.
in 20 years.
This is another funny one. Look at the number there. Okay, right, so demo. So what I've done is I've made a very simple automated theorem prover, all in JavaScript, and it's based on the work of Tim Gowers and Marian Gardner-Sunningham, and the idea is it's a theorem prover where the proof steps used resemble human reasoning as much as possible, so that you can generate human-readable natural language proofs as easily as possible. So this is just a very simple example. Okay, so here it is. Can everyone see that? Okay, a bit bigger. Is that good? Okay, so what we're going to do is we're going to say if we have 3 metric spaces and 2 functions, and they're both continuous, then their composition is continuous. So this is just going to run a series of tactics on it. So it has a waterfall of different tactics, and then if one succeeds, it goes back to the beginning of the waterfall. Okay, but interesting, the thing you should look at is the write-up. So I'm going to do a few steps here. So because I'm using JavaScript, I can use MathJax to get a nice rendering of the equations. That was almost no work to get the equations to work. Because someone's already done it, and this will run anywhere. It will run. Yeah, I can even run this on my phone in a browser. Okay. So I should be. This is a kind of a Tableau thing. So T6 is the thing we're trying to prove. Standard. So we expand some definitions out. Okay. So note how the write-up, we can generate a fairly readable write-up. Using some tricks. Okay. And now I've also got some interactivity in here, so I could apply the triangle rule here if I wanted to. Boom, make it even more complicated. You don't actually need to do it here. And it's also, has a write-up triangle rule. Okay, but I won't do that. And then this is just some internal rewriting, so it can more easily access the result of that hypothesis. Oh, that's it, and we're done.
Could you get it to find the human proof?
The human proof.
Well, it should be characterized continuous functions by converse image of open sets are open sets.
Oh no, it's
and then it's one line.
Yeah, but this is with metric spaces.
It still works in metric spaces.
With absolutely does it. Yeah, but you need topology, and I didn't code that up. But I think this is the kind of proof that that wouldn't be out of place in the textbook. So the hope is eventually, for any automated proof, one might expect to be able to generate something similar to that. Okay, right, so that's the end of the demo. Oh yeah, it's also generating a formal expression here. So this is like a Curry-Howard correspondence style lambda expression. So that could also be plugged into an here.
You've suggested that the theorem prover should bend to the mathematician.
Yeah.
To what extent should the mathematician bend to the theorem prover?
I think the mathematician should bend to the theorem prover to the extent that the mathematician wants to use the theorem prover. And at the moment, they don't seem that keen. So I think, so I believe that we need to go out of our way to make it as readable as possible for mathematicians if we want them to use these tools. Maybe if as they become more powerful, one can get away with having a more specialized formal syntax. So a good example is LaTeX. So with LaTeX, it's awful. The syntax is absolutely terrible, but the power of being able to generate your own beautiful documents is strong enough that the mathematician thinks it's worthwhile to learn to use LaTeX. But that power doesn't really seem to be there with automated theorem proving. It can only ever prove things that the mathematician doesn't really care about because they're at too low a level. And that might just be because the libraries aren't there yet, or It might just be around the corner, but there's still that issue of mathematicians not wanting to use their improvers, and so we have to make it easier for them to use it.
So the interactivity here is pushing buttons, or there are also text boxes where you can enter something?
Yeah, well, this is just
Or there will be
the
demo-
dream is that you kind of have something similar to a text, like a notebook, like a Mathematica notebook, and you can, except with so it's kind of not too far away from how these things work at the moment, where you have some text file, like a dot theory file, and you're getting feedback as you type in, but with more of an emphasis on usability and bending towards being more like what a mathematician would expect to see.
But I was talking about the demo system you were showing.
Oh, this. So at the moment it's just, yeah, you just click run, that's all you can do.
Well, you had these sub-buttons.
Oh yeah, there were a couple of buttons, yeah. So this is very much an early prototype. Okay, so I think that's it. Yeah, we're next. So I really want to work towards making better front ends for these tools. So I made that all myself, including the logic and everything, but I don't think it's sustainable to do that. I want to use these existing tools. I want to make front ends for existing tools that kind of acts as the bridge between mathematicians and these highly abstract ideas about what a prover should be and this formalization. So that's what I want to focus on over the next couple of years. Yeah, thank you very much.
How big is your Facebook?
My Facebook.
Well, of many things that you can
It
actually write down.
It was pretty much the minimum I could get away with at the moment.
But you seem to be quite keen to get the logic of the theorem prover on the front end. But you could also just have an interface that communicates with the server, and
Yeah.
the logic is actually on the server, and then you don't have a restriction when using JavaScript for the logic. Because I think JavaScript, because of its untyped, and people who have be reluctant to use it instead of strongly typed language like Haskell.
Yeah, so that's true. I mean, we can get around that to some extent by having transpilers and things, but I think it would be good to have a central server with all of the theorems already loaded up, and then you just call into the server from the client web browser. That would be great as well. Yes.
It's not even sure there won't be a Haskell compiler to JavaScript in the future. If there's an OCaml compiler, why not?
I think there are some Haskell.
The language, the language in which you program may not be a big difficulty.
But I think the question is whether the search for the proof is done on the browser or on the server. And in my view, I think it should be done on the server. I don't see
Yeah,
why it should be
well,
done on the browser.
Yeah, if you need to have if you have a big database that you need
You
to
have a
go through,
bad connection.
Well, it might.
Well, you have to have a server to software. Somebody has to provide a service. Whereas if you do it on a browser, you just
Let's have
running
Freek
your
and
own
then
thing.
Chris. Oh, Eve, did you have a question? Or?
No, it's okay.
No, Freek and then
Okay.
Chris.
So for me, formalization is just the mathematician's part of programming, in the sense that, of course, contexts are different, but interaction mode to me seems very similar. So in programming, I think Visual Studio as the dominant platform, which doesn't run in a web browser. So do you see a move to web browsers in that context as well, that people do all their program development in a web browser?
So I think people will still mostly develop on locally
Yeah, but
on their
the
laptop.
web
But Visual Studio Code, which I showed earlier, is that is effectively a browser window. So the technology is web technology. It's just running locally. So I think we'll see it more as a UI platform.
Could you run us back to your why slide?
A Y slide.
Yeah, it's always a good idea to know why you're doing something. So those are all driven by the technology. which is fair enough. I mean, that, I agree with all of that actually. But where are your compelling examples? How will you identify the compelling mathematical examples that would convince a mathematician to use anything like this?
Well, I think that this was basically my inspiration was globular. My point at the moment is that it's a more advanced user interface platform, so it will be easier to make nice user interfaces for mathematicians on the web rather than using Swing or whatever.
So I don't know anything about category theory, so your example of globular meant nothing to me, just to admit my ignorance to this audience. And so if you're going to try and convince a mainstream mathematician, you might like to think about identifying some mainstream examples, like your composition of continuous functions examples I consider to be a mainstream example. So how are you going to identify those examples?
Do you mean find examples of theorems that can be proved?
Yeah, I mean there are some sticky theorems in real analysis, kind of every bounded sequence has a convergent subsequence type theorem. Tricky to prove. That's what I think might be a compelling example to a mainstream mathematician. Something they don't have to think about. That's not an advanced area like category theory.
Yeah.
Something from first and second year stuff.
So that's kind of what my
Exactly
one
that
did.
kind
Yeah.
of thing.
So I do have some more complicated examples, but they don't work as smoothly at the moment.
So, yeah, Tom.
Could you say how the write-ups are generated?
Okay, so at each run step, it's doing a particular thing. So for instance, it's taking it. So this first one takes this and puts it above the line, and the idea is the steps are chosen in such a way that each step roughly corresponds to a phrase that a mathematician might write. So it pretty much just has a list of these steps and then transforms them into phrases. And then I do some grammatical tricks, like if you have two lets in a row, it just puts them next to each other with a comma and things like that. But the actual write-up phase is fairly simple. I didn't spend very long on it. The more important thing is choosing these rules in such a way that they reflect reasoning. That's more difficult.
So can you go the other way around? Can you go from that text to this proof?
No, you can't at the moment. What I want to do next is try and implement some of Garner-Salingham's work, which was on the opposite problem of analysing natural language to get mathematical formalisms. And I know we were talking about that earlier as well.
And also, could you take something that is almost in the language and still map it to the nearest charitable proof interpretation?
Not yet.
So you had a question.
This looks like pure HTML.
Yeah, it is. Yeah, I haven't done any styling yet.
Yes. Do you think it might make sense to use some of these open source libraries like Angular,
Yeah,
React.js?
so this is using React at the moment.
It's using React.
Yeah. So everything's immutable and then it's rendering it every time, but in using clever tricks to make sure it's not updating the DOM. That's one of the compelling reasons to use JavaScript is there are all these really modern UI frameworks that have been carefully
This is
built
done
out.
in React, yeah?
Yeah, it's done in React. So I still need to put a style sheet on it to make it a bit prettier.
If you want to think about natural language input, you might want not to go all the way to natural language understanding, but just propose on the side in the menu the sentences of natural language that your system will understand right away. So that will make the adaptability to the user much faster. Instead
Sentence
of
templates.
sentence templates that will correspond to logical rules somehow. But if you propose this, then it may be it may make the interface much with a lower learning curve than you might think. And the problem of understanding natural language has been a big difficulty for the community for a long time. So maybe you want to avoid that.
Yeah. I'm not against using formal languages as well. I just think the formal languages have to be fairly close to the level of abstraction that a mathematician would be used to.
Template sentences are
Yeah.
a cheat in somehow, but it's a useful cheat.
Yeah, no, I totally agree.
There is some work in this direction. The key system, I remember, did something like this.
Key Y.
Key EY. It's an interactive.
And there's also an approach,
Yeah,
Right,
it's an approach as well.
right, which is what's it called, a natural language, controlled natural language.
Yeah, but that's a very restricted language that it accepts. So, of course, all the things that it accepts could be presented as sample sentences or template sentences.
There's also MathNut, which is a fairly complete grammar for proof. And
Is that also MathNet?
MathNut,
MathNat.
MATHNAT, by Humayun.
So there seems to have been lots of this style of tool kind of in the 80s, 90s, and then they all stopped.
Now this is from 2010 or so,
Ah.
or 8. I can give you the version.
So, have you at least scoped out something really complicated that
Yeah,
would
so
challenge you?
the new challenge is the uniform limit of continuous functions is continuous. Because it's got lots of annoying quirks in it.
What about in research mathematics? That's something that's not a textbook mathematics.
Not yet.
Like Ursula showed
I don't know if that's on the
the,
schedule.
Andrew Wiles, analogously and similar to, and then what you need to understand not just the proofs but the constructions. So there's some meta language involved as well. So not just the object language.
There are plenty of challenges.
Good. With that, let's thank Ed.